Then change in enthalpy, that is delta H. H is enthalpy and change in enthalpy is delta H. We know that at constant volume, Q is equal to change in internal energy. Because work will be zero. Work is given by minus P external delta V. If it is constant volume, then delta V is zero. It means W will be zero. If W is zero, then delta U equals to Q plus W. This W is zero, delta U will be equal to Q only. But here we write V just to indicate that it will be equal to Q only if we have volume as constant. So writing QV indicates that it is at constant volume. Otherwise, delta U will be equal to Q plus W. But most of the chemical reactions are carried out in flasks or test tubes under constant atmospheric pressure. So we do the reactions in test tubes which are open. So it is actually the atmospheric pressure which should be constant, not the volume. So for that, the concept of change in enthalpy comes into picture. So delta U is equal to Q plus W at constant pressure. Delta U will be equal to QP, that is whatever is the heat transferred at constant pressure, minus P delta V. This pressure is there and change in volume. There will be change in volume now. Volume is not constant, okay, and pressure is constant. So from here, I will get U2 minus U1. Delta U is actually U2 minus U1. It is a state variable, equals to QP minus P delta V, and delta V is also V2 minus V1 state function. And we can now write it like QP equals to U2 minus U1, QP obviously here, U2 minus U1, and this one goes on the other side, plus P V2 minus V1. So I think that much math you know. Now if I rearrange this one, that I have U2 with PV2, so U2 plus PV2, and I have U1 with PV1, U1 plus PV1. So this term U2 plus PV2 or U1 plus PV1, that is U plus PV, this is known as enthalpy of that particular state. So state 1, state 2, this is known as enthalpy. U plus PV is defined as thermodynamic function enthalpy denoted by H. Hence QP is equal to H2 minus H1. This is enthalpy final. This is enthalpy initial. So H2 minus H1 will give you QP. So QP is actually delta H. H2 minus H1 is change in enthalpy. It is QP. So if you compare it, we said delta U is equal to QV. Okay, means if we keep the volume constant, whatever change in heat is there, whether heat transfer to the system or from the system, whatever change it's, that will be equal to change in internal energy. But if we keep pressure constant, then whatever is the change in heat absorbed or heat released, that will be equal to change in enthalpy. So two important concepts you need to remember. It will help you to solve numericals. Delta U is heat transfer when volume is constant. Delta H is heat transferred when pressure is constant. So although Q is a path dependent function, now you might challenge that here we are saying Q is equal to delta U, here we are saying Q is equal to delta H. Delta H and delta U both are path functions. It is H2 minus H1, means it depends only the difference between final and initial state. Delta U is U2 minus U1. It again depends on only final and minus initial difference, nothing else. So why we can say that here delta U, which is a state function, is equal to Q, which is path function? The reason is we are specifically saying volume is constant. If volume is constant, only then it will act as a state function. So heat will act as a state function at constant volume. Similarly, heat will act as a state function at constant pressure, and that will be equal to change in enthalpy. Okay. So delta H is independent of path, hence QP is also independent of path. QP is also a state function. Similarly, QV is also a state function. So delta H, delta U, QV, QP, all are state functions, but Q is not a state function. If we say just heat, it is not a state function. Delta H is negative for exothermic reaction and positive for endothermic reaction. And it is very simple concept we have already talked about. If it is a system, whatever is into the system, whether it is work, whether it is heat, it is positive. Okay. Whatever is outgoing from the system, whether it is work, whether it is heat, it will be negative. So exothermic reaction means heat is evolved. So this is exothermic reaction. Heat is evolved. It means delta H, which is QP, will be negative. But if it is delta H getting into the system, absorbed by the system, it will be endothermic reaction. It means for endothermic reaction, delta H, which is QP, will be positive. So endothermic reaction, delta H positive. Exothermic reaction, delta H negative. Then relationship between these two entities we talked about, delta H and delta U. Very important formula you will be using very frequently. We know that delta H is equal to Q plus W. For finite changes at constant pressure, we can write delta U equals to QP plus W. So if we are talking about constant pressure, which is normally the case, we do normally the reactions at constant pressure, then this heat transferred will be QP. And some work can be done because delta V is not zero now. Volume can change. Okay, so the reaction mixture can expand, can contract. So there can be change in volume. So W will also be there in that case. We can write W as minus P delta V. It means delta U can be written as, remember at constant pressure, it can be written as QP, that is delta H minus P delta V. Why delta U comes into picture? Delta U comes into picture because some work is also being done apart from heat transfer. So if we are doing any experiment, any reaction at constant pressure, it will ensure that heat transferred is QP. It cannot be QV. But at the same time, delta U appears because some work is also being done. So sum of these two will give you change in internal energy. QP we can write as delta H. So it means delta U is equal to delta H minus P delta V. It means delta H is equal to delta U plus P delta V. This is initial form which in few cases we will be using. Okay, it is not much used, maybe 20% times or maybe 10% times we will be using this one. But if we modify this one, that is the form we will be using very frequently of the same formula. So for two gases A and B, and it is applicable for initial and final state also. Although I have written here two gases, it will be applicable for the reaction also. So for example, if I have a reaction CH4 combustion of methane plus 2O2 will give you CO2 plus 2H2O. So in this case, this is gas, this is gas, this is gas, this is liquid. Okay. So initially I have methane and oxygen, different gases, and finally I have carbon dioxide, different gas. Okay. So it is initial and final case also. But in general, I have written for two gases A and B, PV is equal to nRT. So because PV is equal to nRT, this is ideal gas equation. For gas A, it will be PVA equals to NART. For gas B, it will be PVB equals to NBRT, or maybe in initial state and in final state. These will be the two equations. So if we subtract the first one from second one, so if we do equation 2 minus equation 1, we will get PVB minus PVA equals to NBRT minus NART. If we take RT common, it will be NB minus NA. It means it is change in the number of moles. This is change in the number of moles, delta N. So we can write it as P delta V, because VB minus VA will be delta V. P delta V equals to this one has been written as delta Ng and RT. What is delta Ng? Delta Ng is actually the number of moles of products minus number of moles of reactants. This is the change in the number of moles. So if I take the example, same example I talked about earlier, combustion of methane. Remember, this is only true for gaseous moles. Okay, so as you see here, this is liquid. So if I have to calculate delta Ng, I will calculate only the gaseous moles. Okay, so number of moles in product side, 1 mole here of carbon dioxide. I will not consider number of moles of H2O. Although it is 2H2O, I will not write it because I will consider only the gaseous moles. Okay, so gaseous. So it is 1 delta Ng. In this case, G indicates gaseous only. Okay, so that's why Ng written here will be equal to number of moles of products will be only 1 minus number of moles of reactants which are in gaseous form, 1 here and 2 here, total 3. So it means delta Ng in this case will be minus 2. That's how you will calculate the value of delta Ng in numericals. This is very important, delta Ng RT. Now we can replace P delta V in previous equation, what we talked about here. In this case, P delta V can be replaced by delta Ng RT. So when we replace this, we get delta H equals to delta U plus delta Ng RT. Very important relationship you will be using throughout thermodynamics. And how do you remember that? It is of the form of HURT, H-U-R-T. So just remember, I usually call it HURT formula so that you don't get confused whether delta U is here, delta H is here. This is common mistake students do. Okay, sometimes students write delta U equals to delta H plus delta Ng RT, which is wrong. So remember, everything is positive. First of all, it is plus sign, it is not minus sign, and it is HURT formula. H for delta H, U for delta U, and then RT means delta Ng RT. Solids and liquids do not suffer any significant volume change, means delta V has to be 0 there. So if I go back to this formula, this one, okay, in this case, if I am talking about solid or liquid, the change in volume will be almost 0. So in that case, delta H will be approximately equal to delta U. There is negligible difference in volume. Remember, only in case when all the reactant and products are either solid or liquid, there are no gaseous form. Okay, so if we don't have any gaseous reactant or product, in that case only delta H will be equal to delta U. So in that case, delta H will be equal to delta U when no gaseous reagents or products. When no gaseous reactants or products are there. Now the question, if water vapor is assumed to be a perfect gas, means ideal gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. What is this molar enthalpy change? You know, enthalpy change is delta H. Molar enthalpy change is per mole. Okay, so if it is given as 41 kilojoule and you see it is written as per mole here, okay, because if you have for 2 moles it will be double. So that's why you have to quantify it for particular amount, 41 kilojoules per mole. It is given. Okay, so delta H for water vapor is given 41 kilojoules per mole. And pressure is given 1 bar. Pressure is 1 bar. And temperature is given 100 degrees Celsius, that is 373 Kelvin. All the calculations will be in kelvins for temperature. Okay. The question is, calculate the internal energy change, means delta U. when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. Means what's happening? 1 mole of water, this is liquid form, is vaporized, means now it is gaseous form. That is the first part of it. 1 mole of water is vaporized. So pressure is given, temperature is given, delta H is given, delta U is to be obtained. You will apply the Hart formula. Okay, you will not write in exam Hart formula. I am writing just to make you understand so that you can recall. Okay, you will say using the formula delta H equals to delta U plus delta NGRT. So delta U from here we have to calculate will be delta H minus delta NGRT. Delta H is given 41. Now very important point where students make mistake. It is given in kilojoules and the value of R when you use 8.314, it is joules per mole per Kelvin. So value of R is 8.314 joules per mole per Kelvin, and you can't use two different units. So either you use delta H as 41 kilojoules and then convert this R also to kilojoules, or you convert this delta H to joules. Okay, so I'm using it as kilojoules and I will convert R into kilojoules. 8.314 into 10 to the power minus 3. Okay, if I convert it to kilo, I will have to divide it by 1000, that is multiplication by 10 to the power minus 3 kilojoules per mole per Kelvin. And what is delta Ng? It is important to understand what will be the value of delta Ng. This is the reaction. In this case, delta Ng is gaseous moles of product minus gaseous moles of reactant. Now here gaseous moles of product 1, because here it is in gaseous form. Here you don't have any gaseous reactants, means 0 moles. So it will be 1 minus 0. Okay, water is vaporized, final 1 mole gaseous, initial 0 moles gaseous. R 8.314 into 10 to the power minus 3 kilojoules per mole per Kelvin, and temperature 373. So when you solve it, you get the value 3.096. This value, when you simplify, 3.096. This 1 is because delta Ng is 1 minus 0, that is 1. So when you solve it, you will get 37.904 kilojoules per mole change in internal energy. That is the answer of first part. Now the second part. Second part is 1 mole of water is converted into ice. Now there is no gas. The reaction in second case will be you are converting the water to ice, means liquid to solid. And in this case, we will apply this formula. We can apply the other formula also. We can apply this formula also. Okay, I will show you that you can apply any formula in this case. So if we use this formula, is there any change in volume? No, we talked about that there is hardly any change in volume if there is no gaseous reactant or product. So liquid to solid will not result in any significant change in volume. Means this delta V will be 0. And if delta V is 0, delta H will actually be equal to delta U, or delta U will actually be equal to delta H. So in this case, it means you can write delta U will be equal to delta H, that is 41 kilojoules per mole. You can apply the formula delta H equals to delta U plus delta NGRT. In this case, delta Ng will be 0. Why? Because the final product, gaseous product 0, initial gaseous product 0. We have only liquid and solid, so gaseous moles 0. So delta Ng will be actually 0 minus 0, that is 0. So delta H will be equal to delta U, or delta U will be equal to delta H. Again, okay, so delta Ng is 0. So delta U will again be 41 kilojoules per mole.